to the 13th session of Electromagnetic Theory and Interference course. In this session, we will learn about how to find the electric flux density due to a point charge, and we will find the relationship between electric flux density and the electric field intensity, as well as we will see Gauss's law through which we will arrive at the first Maxwell equation. So let us start. So first we are going to consider a point charge, okay, that is located at our origin, and we are aiming to find the electric flux density d vector at a distance r from the point charge, okay. And we have considered an imaginary sphere where from the positive charge the flux lines are coming out, originating from there. Okay, and it is coming radial outwards, right? So we already know the magnitude of electric flux density is nothing but total flux per total surface area. And we already know that flux is equal to the total flux is equal to the charge, right? And the surface area of sphere we know that it is 4 pi r square, and if you substitute the above relation in this formula, we will get d vector is equal to its magnitude is equal to q by 4 pi r square. So the unit vector, if you see, it is radially outwards and it is normal to the surface. At any point on a surface it is normal. So the vector form of electric flux density is defined like this: d vector is equal to q divided by 4 pi epsilon r square into ar cap. Okay, because it is along the radial, that is how the flux is coming out in the same direction. So ar cap, coulomb per meter square flux density. That is, coulomb is related to charge, surface area is measured in meter square. Now let us see the relationship between electric field intensity and electric flux density. So in the last few sessions, we have seen that electric field intensity at a distance r from the point charge q is given by q divided by 4 pi epsilon naught r square into ar cap. But now only we have found that electric flux density is equal to q divided by 4 pi r square into ar cap. So if you see the relation, we can find that d divided by e vector. So all the common terms will get cancelled. I will get epsilon naught as answer, because it will be 1 divided by 1 by epsilon naught. That epsilon naught will come to numerator. So d is equal to epsilon naught e. So we can find that d and e are related through the permittivity of the medium. So this is the permittivity of free space, right? If it is not a free space and it's having some other medium where we are placing our charge, means the d vector turns out to be epsilon naught into the relative permittivity and the electric field intensity. So d vector is equal to epsilon naught e vector. This is our final relationship. So from the above relationship, we can find some observations. First, the d vector and e vector are having same direction. Both are having in same direction, and they are related to permittivity of the medium where the charge is located, d. And one more thing, this equation is not only applicable for point charge. This relation is valid for any type of charge distribution, general charge distribution. And these two relations of electric field intensity and electric flux density due to point charge, we can find that electric field intensity is a function of the permittivity epsilon, while electric flux density d vector is not a function. So now let us learn about the Gauss's law. From where we will arrive the first Maxwell equation. And to do that, we have to apply the divergence theorem here. And now let us see what the divergence theorem states. So here we can see that the total outward flux of a vector field. So we just now saw that flux is nothing but lines of force, right? So the total outward flux of a vector field through a closed surface is equal to volume integral of the divergence of the same vector. So it is going to relate surface integral of a vector field to the volume integral of the divergence of same vector. This is my divergence theorem. So From the Gauss's law, we already know this relation, but this is the Gauss law statement only. Gauss has stated that the total electric flux through any closed surface is equal to total charge enclosed by the surface. Psi is equal to Q enclosed, we already know. If I want to find the total flux, I have to integrate the differential flux, right, over the closed surface. So same I am doing. Instead of d psi, we already know the relation. Flux density is flux per unit area. So I can take d phi as d vector dot ds, right? And that is equal to the charge enclosed as per the Gauss's law statement. The charge enclosed, I can write it in terms of volume charge density rho v into dv. So I am taking the last three expressions in this equation. Q equal to uh, closed surface integral of d dot ds, that is equal to volume integral of rho v dv, right? So I am taking the middle term and I am going to apply the divergence theorem here. So what a divergence theorem states, so I can replace the surface integral, okay, of a vector field by the volume integral of the divergence of same vector. So instead of a vector, I am replacing it with the electric flux density. So comparing above two equations, we can about two volume integrals, especially volume integrals. If you see surface integral is same. Volume integral, if you see del dot d is equal to rho v. This is my first Maxwell equation. So